Good afternoon, everyone. My name is Yong-un Choi, and I'm glad to introduce my work, optimizing energy efficiency of browsers in energy-aware scheduling-enabled mobile devices. I briefly introduce the authors, and I'm the first author and second author, Sung-hoon Park, and my advisor, Professor Ho-jung Shah. During the 10 years, the mobile AP has been 20 times faster and the display resolution has been 10 times higher, but the battery capacity has only doubled. Due to these unbalanced advances, efficiently using the limited energy is a very important problem. Particularly, a web browser is one of the mostly used applications, so reducing the energy consumption of the web browsing becomes more critical. Energy optimization of mobile devices is mainly targeted to the CPU. Web browsers typically operate by fetching web resources through the network and processing them to construct the web page and finally drawing the frames on the screen. As most of these processes are executed by the CPU, the energy consumption of web browsing is highly dependent on how the CPU frequency is adjusted. Recently, new CPU DVFS paradigm, energy-aware scheduling, was suggested, also called EAS. EAS combines the CPU scheduler to the DVFS governor, so it can determine energy optimal coherent frequency at the same time before assigning a task. A computational resource required by the task is represented as a capacity, and the CPU frequency is determined by an accumulated capacity on the core. If the capacity of a task is evaluated intentionally higher, then the processing of the task can be accelerated. This feature is called capacity clamping. How high the capacity will be evaluated is determined by the clamping factor. EAS enabled the systems to improve the foreground app's quality of service by using this capacity clamping feature. Then, how to energy optimize web browsing for EAS-enabled mobile devices? We found new opportunities through our observations. We first noticed that the modern browser consists of multiple processes playing different roles, but all the processes are executed quickly. We suspected whether these processes can run at different speed, respectively, without increasing the page load time, that is the higher level quality of service of the browser. And to verify this, we divided the browser processes into two groups, one for the process handling the web resources directly and the other for the rest. Then we found the lowest clamping factor for each group without increasing the page load time, and the result shows two lessons. First, different processes can be processed at different speed by using the different clamping factor, and second, optimal clamping factors depend on the web page. Second, we focused on the behavior of the browser after loading. After loading and when user input occurs, the browser handles the input and draws the frames. After handling the user input, however, the browser's task does not need to be accelerated because the frame rate is fixed no matter how quickly the task is done. To verify this, we experimented with a specific scenario and implemented scenario-specific script which applies the lowest clamping factor to each group without frame drops. The results showed that the lowered clamping factor leads to the lowered CPU frequency, so we can learn that the processes of the browser can be processed slower after loading. From our observations, we learned three lessons. First is that different processes can be processed at different speed, and second is optimal clamping factors depend on the web pages, and the process can be processed slowly by using lowered clamping factor after loading. So these lessons lead to one conclusion, that we should control the clamping factor of the browser's processes dynamically. Our approach is to control the clamping factors of the processes respectively by using the information inside a browser and system. We classify browser processes into two groups, foreground and background, and apply different clamping factors to each group. But how to control these factors? To adjust clamping factors optimally, we should consider the effect of the current decision on the page load time, which can be measured after loading. Reinforcement learning is a representative technique for solving this kind of optimal control problem. To apply reinforcement learning to solve our problem, we define the core element of the reinforcement learning, the environment, state, reward, and action based on the information available from the browser and mobile systems. Also, we carefully designed and tuned our model to have a little overhead. More details are in our paper. To realize our approach in mobile systems, we propose WebTune. WebTune requires a slight modification of the browser and kernel to collect the data and add the process group. The core operations of WebTune are executed in the background service, which includes reinforcement learning and controlling the clamping factors. And this structure allows WebTune to be applied only while the browser is running, thus minimizing the impact on the behavior of Android kernel and the web browser itself. We implemented and evaluated WebTune on the 2 Android reference smartphones and experimented with real websites by using the web page replaying and network simulating techniques, and power consumption was measured by the monsoon power monitor. We first evaluated the energy saving effect of the WebTune, and the results show that the WebTune successfully lowered the overall clamping factors of browsers processes, and this leads to the lowered overall CPU frequency and finally leads to the energy reduction. And we also evaluate the quality of service with 4 criteria: page load time, latency from click to the first frame rendered during the loading, and the speed index, and the frame drop. And from the result, we could not observe the meaningful QoS degradation. We also evaluated our work in various aspects, including the overhead, training speed, and the effect of caching, in comparison with the other supervised learnings, but skipping here. In conclusion, we observed that the energy inefficiency while running the web browsers in real EAS-enabled smartphones, and that implemented the WebTune to save the energy by process classification and using reinforcement learning. And the WebTune successfully saves the energy about 13 to 22%. And I'd like to finish my talk by introducing our future work. And we are planning to extend our work to the EAS-disabled systems that the latest Linux kernel has been equipped with the utilization clamping, which is similar technique to the capacity clamping, so that we think that our work can be extended to the EAS-disabled systems. And also we are planning our work to extend to the web browser-based OS such as Chromium OS. Thank you for your listening.